Anyway, welcome to the Royal Astronomical Society St. John Centre. I was going to say RASC, but I already said Royal Astronomical Society of Canada, so why repeat myself? I'm Gary Diamond. I'm the president of the centre, and I want to welcome you to our monthly meeting. I hope everybody's had a good month and got out observing. There's been a couple of good nights of observing. And let's move on to our speaker tonight, because I'd like to get into the speaking part of the program as fast as possible. And we'll do that by having Jim introduce our speaker for tonight. Are you there, Jim?
Yep, I am.
I guess I have one question. Can I? Yeah, I can share my screen. That's awesome. Oh, it says that the host disabled the participant screen sharing. Could I get that so I can show my presentation? Oh, there you go. Should work. Let's see. So does everybody see my slide, which is entitled Space Surveillance and the Intelsat 1002 Servicing Mission? So as my the title states, we're going to talk about two things tonight. Space surveillance and the experiment that actually spawned this, I think, presentation tonight. It was the characterization or the observation of the Intelsat 1002 geostationary satellite. And I'd like, first of all, to acknowledge all of those that participate in the elaboration of either this presentation or the elaboration of some of the data that's going to be presented tonight. So first and foremost, my co-presenter tonight, Mr. Jim Johnston, who's been, well, instrumental to the success of this experiment. It's not yet completed. We still have, I still have a ways to go. I need to report on the findings and complete the data analysis, but all of this wouldn't have been possible if Jim wouldn't have positively answered the call last summer and provided me with all of the data that he did in the last 8 or 9 months now. It's amazing how time flies. Next up, I want to underline Mr. Jack Warrow's contribution. He's a co-op student from York University who's on a 1-year co-op term at DRDC Ottawa. He's a 3rd-year engineering student at York University under Professor Regina Lee. And he's been phenomenal. He basically came into into the group in January, and he's actually the person who's processed all of the data so far. So I provide the guidance, the mentorship, but he's he's the brute force that actually produced some of the figures tonight, and who's going to produce a lot of the analysis for the report that we're going to be finalizing. Also, I want to underline Captain Shane Rydell. He's a scientific officer. So much like I was a science officer almost 20 years ago now, he's joined our group, and he's also participating in the processing of the data. So with that, I'll get going. So actually, I'll get back to the title. So tonight, when Jim first wanted or proposed the idea of discussing the experiment with you guys tonight, I thought it was a great idea, but over the years, I've noticed that when I start talking about specific things I do, people have a lot of questions about space surveillance in general, and that's not an activity that's widely known. So with that, I decided tonight to give a bit of a primer on what space surveillance is, what it does, and that's going to lead into the Intelsat experiment that we've conducted. So that's the agenda tonight. Background, we're going to talk about space surveillance, and then we'll jump into the Intelsat 1002 characterization experiment that we've been doing since last September. So I start the presentation with the question, how many of us rely on space capabilities? And when I talk about space capabilities, or when you hear people, you know, defense people or government people talk about space capability, they really mean satellites. How many of us rely on space capabilities? And if we were in a nice meeting room, I would ask people to raise their hand. And actually, well, I can see some of you. you can do so. But typically, the response has been that not a whole lot of people raised their hands. And not a whole lot of people realize that they actually use indirectly satellites. So to that, I say, if you woke up in the morning and you looked at the news, well, depending on what your cable distribution service is, you probably got Satcom TV. If you looked at the weather and you wanted to know, well, what's the weather going to be like today, tomorrow, to start making some plan, you indirectly use satellite service. If you took a flight to go somewhere, or if you're on a boat, on a ship, to go anywhere, I'm talking commercial ships, even small ships now, sailboats, they're using satellite services, navigation, but also awareness about what the other ships in the areas are, or what other aircrafts are going to be in the area. In our cars nowadays, GPS, I don't go anywhere now without my GPS. If I used to look at a map, nowadays, if I don't know where I'm going, I'll punch in the address, and I wouldn't say blindly follow my GPS, but I give it a lot of I guess, confidence. I have a lot of trust in it. And then finally, our banking infrastructure. Every time you use the ATM, you might not realize it, but the timing that is actually on that piece of paper has been synchronized to the GPS satellite system. So that being said, all of us as ordinary Canadians use satellites indirectly or directly. At least it's been quantified between 7 to 15 times a day. Now, I don't put a lot of faith in those numbers, but you know what, as a rule of thumb, it sounds about right. Next up, are there any other users of satellite services? So I talked about individuals, but are there bigger users, industrials or government users? And it turns out that, yeah, a lot of people, a lot of organizations, a lot of services depend, not only use satellite services, but depend on space capabilities. Your energy grids are all synchronized on GPS time. Do they have backup? If GPS fails, of course they've got backup, but the primary system is GPS. Your cell phones, all the time stamping, all synchronized to GPS. We've already talked about the bank machines, but if you think stock markets, all of this financial trading system, all time tag, well, not only GPS for the timing, but also the comm system. Some of the backbone may rely on geostationary satellites. Ship radars, gyro compass, and so on. Basically, it goes on and on. First responders, firefighters, police, ambulance personnel. And then at the bottom, you'll see I've got Earth observing. That falls into the category of not only just for the scientists, but also for disaster management. I'm sure you remember the floods in Winnipeg, the floods in southern Quebec and eastern Ontario a few years ago. One of the first things that planners want to do, the disaster management planners want to do, is have maps of the current situation as it stands now compared to how it was in the past. And the only way we can get very accurate maps of images of what's going on now is by using assets in space. So that said, everybody depends on space to some degree or not. And that explains why, if you look at this graph, and this is a figure, and essentially what you've got is the number of objects in space as a function of year. So if you look at the first object that was launched in space, 1957, Sputnik, we look at 1957, we're almost down to 0. And one thing that we note is that the number of objects, so the total number of objects, and that's the, sorry, I don't know my colors very well, but that's sort of dark brownish red, the line at the top. And you can see that we're seeing this steady growth, and we've seen this steady growth almost at a constant rate going from the 60s up to about, I'd say 2008, right? And During that period, people, well, governments mostly, major commercial corporations were realizing the benefits of space and launching space assets into space to exploit that. And then if you look, starting in 2007, there's this massive jump. And what's that jump? Whoops. It's a Chinese anti-satellite test. In 2007, China, depending on the literature that you read, but the widely accepted one is that they wanted to show the world that they were a credible space power. They wanted to show the rest of the world that they had the capability to negate space assets. So they decided to shoot a missile at their own satellite, a defunct Chinese satellite, to see that we could effectively destroy a satellite. The unfortunate consequence of this event was a very large jump in the number of space objects that were now being tracked. And the large increase in space object is not active satellites, it is space debris. And actually, if you look down at the lines below, you've got a breakdown of what these total objects are. Fragmentation debris, that's exactly what it means. It's space junk, right? It's debris anywhere from very large pieces like unused or unoperational satellites that have extended their lifetime, to objects that could be as small as about 10 centimeters. So something that I'm holding like this. Anything under than, on average, 10 centimeter, not being tracked right now. So next up, you see there's this big jump in 2009. And here it's called the Iridium Cosmos collision. So this was not an active anti-satellite test. This was actually an accidental collision in space. An active satellite, Iridium American operational satellite, collided with a dead Russian Cosmos satellite. It generated about 2,000 pieces of debris. We can see then the line sort of tapers off or stays constant for about 3 to 5 years. And then now, if you look at the complete end of the figure, it's starting to increase, but this is not a linear increase. Actually, it's starting to be an exponential increase. And that's not an error. Actually, the cost of launching is going down. So more and more companies are launching stuff into space. And you might, well, actually, we hear a lot about the amateur astronomers and the professional astronomers starting to voice their concerns that there are too many satellites out there. They're polluting the skies. So this is corresponding to companies like SpaceX, Intelsat that are planning to launch constellations of thousands of satellites. And we're now at the start of this exponential growth curve. So I'm showing this graph to make the point that space is not something that other people use. Space is something that we all use on an individual basis, on our day-to-day basis, as well as collectively. The bottom line for me telling you this is that space is considered the invisible utility. And for the last, I guess I've been now working in the space field for the last 20 years as part of a defense team member. And although it's not officially recognized, it's unofficially recognized that space capabilities are part of the Canadian critical infrastructure, meaning that the government is keenly aware of this infrastructure and has to make sure that it stays functional for the benefit of Canadian society. And this is why, if you look back to 2017, the D&D space policy that was published then, made a big deal out of space. If you look at all the previous defense policy papers that were published before then, space barely got a mention. Strong, Secure, Engage, when published in 2017, had about, I believe, 150 mentioning of the word space in it. And here I've just underlined a few of the major space references that are in this document. And this just goes to show you how seriously the government of Canada is now taking space. And by taking space seriously, space surveillance is that activity that's going to allow us to keep informed on what's going out there. So I guess, why is space surveillance needed? Okay, we all use satellites, so what? As long as they're up there, why do we need space surveillance? So before 2007, the reason we needed space surveillance, or to keep track of all the objects up there, was that, well, typically, I'll actually jump to the bottom part of my slide deck there. The emphasis of space surveillance was focused on what we called catalog maintenance. So making sure that we kept track of what was in orbit, to essentially keep tabs on everyone, but not keep tracks on everyone because we were interested in knowing what they were going to do. It was mainly for space mission support objectives. So when can I talk to my satellite? When can I download data from my satellite? If I'm planning a mission in this orbit, what are the other users of this orbit? There was a bit of collision avoidance, as I just mentioned, but that was not the focus. It's mainly to know essentially what's going on up there and how can I use it to plan my mission. From a D&D perspective, or a military perspective, there was also an emphasis on the reason we wanted to keep track of all the objects orbiting the Earth was to make sure that if there was an ICBM coming at us, we could differentiate between the ICBM and the objects in orbit. We didn't want, let's say we got this new object in orbit, we wanted to make sure that, it was indeed a satellite orbiting the Earth and not an ICBM, which borrows trajectories in space to get to their target. We wanted to make sure we could differentiate between the two. Before 2007, and if you recall what I said, 2007 was the year that the Chinese conducted their ASAT test. The numbers of nations operating in space were fewer in numbers than today, mainly the major space powers and sort of your G20 type countries. And we were mostly limited to national governments. There were some major corporations, but you didn't see universities, you did not see, well, you saw perhaps like big missions, but you didn't see, universities doing just space missions for, well, the fun of, or just the curiosity of doing a space mission. Notwithstanding the harsh physical environment of operating in space, the Earth orbit environment was actually considered benign. And here, what I really want to say was that there was no adversarial behavior in space. If you launched your satellite in space, you were pretty sure that no one was going to come out and touch it or look at it for that matter. So here, before I move on to the post-2007 situation, I'll take a step back, or maybe just a sideline here, and I'll say, how do we define orbit? So I keep saying we'll keep track of satellites. How do we take that? Well, actually, what we're interested in when we do space surveillance is defining and updating what the orbit of a particular object is. And typically we defined, or not typically, we defined based on, I guess, the laws of physics, that orbits are defined by 6 parameters. So if some of you took physics in your earlier years or at school, you'll remember perhaps that we can define an orbit by the Keplerian elements, which had 6 parameters. And here, the figure on the right, you see what those 6 figures are. We can also define them with the position and velocity vectors. Or if some of you, decided to track satellites just for the fun of it, you've probably used 2-line elements. And what are 2-line elements? Well, there are 6 parameters to define the orbit that you can feed into what we call the SGP4, so Special General Purpose Propagator model, essentially to draw out that orbit if you wish. So what does a 2-line element set look like? Like this. If you're thinking to yourself, well, geez, that looks a lot like, 1970s or 1960s sort of basic or Fortran code, that's exactly when the 2-line element sets were created. They were created to be on these cardboard punch cards and essentially fed into a NORAD computer way back when. Unfortunately, with DoD and D&D, things advance at a glacial space. So we're still using TLEs to this day. But essentially, if you parse that through the two-line element set, you'll find your 6 orbital parameters. So when we do space surveillance, when we look at objects, for most of the time, the objective is to define new two-line element sets like you see on your screen today. So now you might be wondering, so once we've observed an object, why do we have to keep on tracking that object and revisiting this object again and again and again? The answer to that is, well, not that complicated. If, you know, the Earth is not a perfect sphere, okay? It looks like the object that you've got on the right of your screen. When I did my master's, actually, my astrodynamics teacher had a pretty good analogy for the Earth. He said, imagine a 50-year-old man, a bit light on the top, losing his hair, and a bit round around the belly. So that's exactly what the Earth looks like. It's a bit flattened, so we're not getting these perfect orbits. They're getting perturbed, so they're changing continuously. Moreover, you've got areas on the Earth where you've got these mountainous regions, so more mass attracting the satellite, and we've got these areas where there's, you know, very deep, like ocean, where there's less mass, so there's going to be less gravitational accelerations or attraction. So this is perturbing the orbit. Depending on the altitude of your satellite, you've got the atmosphere, which is going to induce drag. You've got solar radiation pressure, which you might think is minute, but when you're operating in space and you've got very large solar panels, it's got a significant impact. And satellites also maneuver from time to time. So this explains why we have to track satellites over and over again. And finally, if you recall, I said TLEs, the two-line element set, feed into what we have, well, a propagator, right, to sort of draw out that orbit, the SPG4 model. Well, the accuracy of this model is not perfect. Typically, orbits generated by the SGP4 model will have about an uncertainty of 1 kilometer. So essentially, if you look at the figure on the right, you see these green oval type balls. The center is, the satellite's believed to be in the center, but we've got an uncertainty as to, we're not quite sure where the satellite is within that bubble. Typically, with the SPG4, we've got the size of that bubble at its longest is about 1 kilometer. Depending on the object and the characteristics of its orbit, so if it's very low and there's got lots of forces like drag acting on it, the uncertainty is going to increase at a rate of about 1 to 3 kilometers per day. So if you don't revisit that object very often, essentially, eventually you're going to lose it. So that's why we need to, well, do space surveillance and keep track of our objects. So now let's get back to, we just talked about the situation before 2007. What happens in 2007? Well, as you can imagine, when I alluded to it earlier about the Chinese anti-satellite test, new challenge arrived. If it were just for the Chinese anti-satellite test, it wouldn't be too bad because from that, I guess we can call it experiment, there was a lot of fallout and there was a lot of lessons learned, and everybody in the international community recognized that anti-satellite tests are bad. They're not good for anyone, even the country or the nation conducting the test. So ASAT tests are a challenge, not the only challenge. Post-2007, the biggest challenge now are new space technologies are changing the way we need to perform space surveillance. We're seeing smaller and smaller satellites. You might have heard of CubeSats, satellites that are no bigger than the object that I'm holding. Actually, I should have thought about it earlier. Actually, if we've got some time at the end, I'll show you. I've got a 10 by 10 by 10 engineering model of the CubeSat that was launched by the University of Toronto. They're small, they're hard to see, but we still need to track them. We're seeing multiple satellites flying in tight co-located clusters or formation flying. We're seeing satellites that are using all-electric propulsion system. In the past, with liquid or just impulsive propulsion. Basically, you'd have your satellite. It then would just activate its booster for a few seconds, and then its orbit changed. You could calculate the new orbit then. Now, with objects that are continually thrusting, essentially your orbit is changing all the time, meaning that you have to track these objects almost continuously. And then finally, and the main topic of our presentation tonight, on-orbit servicing technologies are appearing, and they're straining classical space surveillance system. We're seeing now objects getting very close to other satellites for, well, on this case, on-orbit servicing, but you can rapidly imagine where we could use this technology for good, but it could also be used for, not so good purposes. Another threat and another reason why we're doing space surveillance is space debris. And space debris, whereas in the past they weren't too much of a threat, now they're posing an increasing threat. And just think back to the figure that I showed you, right? With 2 events, we jumped up almost by 5,000 objects. And now that we're seeing an exponential increase of operational satellites, the risk of collision is increasing. Therefore, the risk of seeing more space debris from these potential collisions are increasing. I've talked about what space debris were, but not only are there shreds or fragmentation debris from satellite collisions, but you've got dead rocket bodies. So we launched stuff up there. We'll have the lower stage of the rocket that falls back to Earth, but you'll have the upper stage that once it's delivered its payload in orbit, will basically inject itself into what they call a graveyard orbit and remain around the Earth for very long periods of time. We've got mission-related debris, so sometimes cover caps of telescopes are ejected and basically just remain in orbit. Perhaps on a more funny note, astronauts working on the ISS, I believe it was like in the 2005 timeframe, dropped a hammer from their space tool bag, and that became a piece of debris. And perhaps you've heard of this, or you saw that a few years ago when Elon Musk and SpaceX tried their biggest rocket. They basically launched, I believe this was the first Tesla car that they built, into a sort of a solar orbit. So this guy's now driving around the solar system and is going to be for a long time. So why are space debris dangerous? Well, debris, as I said earlier, and satellites for that matter, will remain in the orbit where they're typically generated. And that means ultimately they remain where the satellites are. And although space is big, it's humongous. Usable space for space mission is pretty limited, and they're limited to what the regime that you're seeing on your screen. We'll have the low Earth orbit, which basically anything between 400 kilometer to about 1,000 kilometer orbit, any inclination. We've got the MEO, so mid-Earth orbit, at about 12,000 kilometers, and that's where all of your global positioning system and other national navigation systems lie. And then you've got the geostationary orbit. This is where you place a satellite and it's got a rotation period that matches the Earth's day rotation. So essentially, to an observer on the ground, the satellite looks like it's the word geostationary. So although the volume of space is quite large, the places where we can have useful orbits for our purposes on the ground are quite limited. Where we've got satellites, we've got space debris, and if we've got space debris, they pose a threat. And in orbit, typical speeds in low Earth orbit, about 7 kilometers per second. So I live in Kingston, Ontario, a town of about 120,000 people. I'd say the size of the city is about that, 7 to 10 kilometers. So to cross the city on a good day takes me about 35 to 45 minutes. If I were a satellite in LEO, 1 second. In GEO, the speed, if I remember correctly, are about 3.5, 3 kilometers per second. So still very fast. And here what you've got is that small pellet, a 1.2 centimeter pellet, was launched at a velocity of 6.8 kilometer into this aluminum slab. Look at the damage that it done. So even a fleck of small debris of satellites, hitting a satellite could potentially take it out of action. This is why space debris are such a threat. Right now, if you remember correctly from that figure that I showed you earlier on, there are about 20,000 pieces of space debris larger than 10 centimeters. And here I'll underline larger than 10 centimeters. Compared to we're now at 2,000 satellites. This is about a bit dated, but still that's a 10-fold increase between the number of active satellites and the number of space debris that we can track. It's estimated that there are between 500,000 and 1 million pieces of space debris between 1 to 10 centimeters out there. It's unbelievable, and it's getting worse. So that's why we're doing space surveillance, keeping track of the stuff that is in orbit now, and working on sensors to allow us to track the stuff that we can't see at this time. I'll skip that. How am I doing for time?
Good. You got lots of time.
Okay, great. Great. So I guess obviously the more objects there are, the higher the risk of collisions. In the community, we refer those as typically conjunctions. Conjunctions, well, actually conjunctions are, we estimate that there's going to be one. You either have a collision or then you don't. But conjunctions are typically before, when we're making our models and say, okay, something's going to happen. We're predicting that there's going to be a conjunction at that time. Conjunctions do not, for the most part, do not necessarily always translate in collisions. But this is what it looks like, right? Surely there aren't many collisions. Typically, that's what the question I'll get. But you guys have now seen, the number of space debris, limited number of usable areas where we can use satellites. So that ends up like this. So when we're flying, this is a conceptual image of NeoSat satellite that the RDC built along with the Canadian Space Agency, or at least we contracted the company to build it, and we're now operating it. But this is, on any given day, what the environment around NeoSat looks like, the number of objects that there are in proximity. Clear and present danger, more to the point. So unfortunately, these movies, I couldn't get them to work today. I have a bug with, I don't know, the slide deck or the version of PowerPoint I'm using. But some of you might be familiar with RadarSat. RadarSat was the first radar satellite that the Canadian Space Agency launched, I believe, in 2000 or 1995. Shortly after the Chinese ASAT test, RadarSat had to maneuver because there was a high likelihood of conjunction with one of the debris from that collision. And I was told that by the operators that over the years, RadarSat had to do a few more of these maneuvers to make sure that to lower the risk of collisions. Another Canadian satellite that basically came close was Sapphire. Sapphire was the first D&D satellite, or the first Canadian Armed Forces satellite launched in a very, very long time. And shortly after its launch, on 30 July 2013, so about not even 6 months after its launch, Sapphire narrowly missed a fragment from a DSSP American weather satellite. It was evaluated that the miss distance was 44 meters. So in space, that's quite close. And the relative speed was 15 kilometers per second. So if you think back to that slab of aluminum that we saw with that little pellet going at 7 kilometers per second, this was twice the speed. Had the collision occurred, our 6-month-old satellite would have meant that here they say $80 million investment. But if you factor in the ground segment that was built to support that, you're looking at about $100 million investment down the drain by a fragment of a dead satellite. And this picture shows, close approaches to all of the Canadian satellites between 2010 and 2013. Over 1,400 events. And this is not getting any better. So this is why DND and its allies are conducting space surveillance to essentially keep track of that. And when we can, if we're in the position to maneuver or let the operators know that they need to maneuver, we let them know. So what can we do about it? There's a lot of stuff out there. Chances of collisions, are non-negligible. But what can we do about it? Well, the first thing is minimize the stuff that we leave up there, right? We can deorbit stuff. So here we've got a picture of the Mir space station, and some of you may recall in 2001, I believe the Mir space station was deorbited over the Pacific Ocean. Chinese did the same thing. China did the same thing a few years ago in 2018 with their first space station. And the flip side is sometimes satellites are way too high. They've got too high of an altitude, and there's not enough propellant left to deorbit them. So what they'll do is they'll push them higher into what we call graveyard orbits. Obviously, once these graveyard orbits start being more populated, you're getting more and more risks of collisions. I'd say recently, over the last decades, the international community has come together and said that, we're going to impose, or as much as they can, a 25-year limit. If you're going to put something in space, you are going to deorbit it. And as such, from now on, every time that the Canadian government licenses a Canadian company or even a Canadian government organization such as DND, the Canadian Space Agency, allows them to put something in space, we have to show a plan how we're going to deorbit that object after 25 years. I would imagine for geostationary satellites, how they're going to put them into graveyard orbits. But unfortunately, that's not enough. So that's why we keep needing to track and monitor everything that is launched. So tracking everything, not one single nation can do that. I think the only nation on the planet that can try the challenge is obviously the US with their space surveillance network. They've got sensors distributed all over the world, but even then, they recognize that not any one country can do this by themselves. And this is why the US, along with its closest allies, typically the Five Eyes, but now that's been extended to the nations of the combined space operations. So we're seeing Germany, France, outreaches are being made to Japan and other nations to essentially join sort of a coalition effort to pull our efforts together so that we can try to combine our assets to track what's up in space and manage. Canada, as one of the closest allies to the US, we've been collaborating with the US on their space surveillance network since almost the get-go, since the 60s. In the 60s, we hosted two space surveillance sensors, one in Cold Lake in Alberta, and another one in St. Margaret's in New Brunswick. And these sensors, they were optical telescopes, I believe, Baker Nuns, so close to 1 meter, film cameras, and they were tracking satellites night after night when it was clear, and they provided data to the SSN until 1992. From 1992 to about 2005, there was a bit of a gap there. We had the budget cuts, but DND still wanted to be a credible partner, a useful partner to the American Space Surveillance Network, and rapidly came up with plans of coming up with its own sensor to restart providing data to the SSN. What's not shown here is that in the 2000s, DRDC, in support of the Canadian Armed Forces, established what was called a concept demonstrator, so ground-based optical telescope one in Suffield, one in Valcartier near Quebec City, to provide data to the SSN while we waited for Sapphire to get on orbit and be an official contributing sensor to the SSN. And for a short time, the Sapphire, and still to this day, I believe, is the only non-US space-based telescope providing data to the Space Surveillance Network. As it's going to rapidly change as the UK, Australia, New Zealand, and our other allies are rapidly now providing sensors. We also have Canada and other sensors that I mentioned earlier, Neosat. That's an experimental sensor. It doesn't provide data to the SSN, but we're using it to essentially inform what's going to come after Sapphire and future projects. So when I talk about optical sensors, so that's military speaks for a telescope with an ICCD camera in the back. So what you see here are, well, the dome in Suffield to your left, and then to the in the center here, that's the dome in Valcartier at our laboratory in Valcartier near Quebec City. And then, if I'm not mistaken, the one that you see to the right is our observatory that we're using here in Ottawa to observe satellites. As you can see, this is not, very expensive. We're not sort of professional astrophysicist grade observer. We do observations with 14-inch. This is a C11 or C14 from Celestron, Apogee camera, and a software BISC Paramount ME. How we collect the imagery, two modes. And I'm talking to those because I'll be talking about how Jim collected the imagery later on. So the first mode is sidereal star-stare mode or star-stare mode. And essentially what we do is we track stars where we're expecting the satellite to be. And based on the satellite catalogs, the TLE that we've got, we know where the satellite is going to be at what time. And then at a given time, we start the exposure. When we start the exposure, our stars are going to essentially look like point sources, which all of you are familiar with. But your satellite is going to look like a streak. And then when we essentially analyze that streak, we can essentially compare it to where we were. Well, we basically mark the endpoints, and that allows us to get the astrometry off the streak, where it's located, its RA and DAC, and then from this information, we can determine its orbit. And then we can compare it to where we were expecting the satellite to be, and that can tell us about the perturbations that occurred, or if there were maneuvers, and so on. Next up, track rate mode. Track rate mode is we're still using the TLE or the element set that we've got for the satellite. We're going to go in the area where the satellite is. We essentially wait for it. So we're parked. When the satellite is in the field, the center of our field of view, we start tracking on the satellite. Once we start tracking, we essentially start exposing. So now, contrary to the star-stare mode, where our stars appeared as point sources, here the stars will appear as streaks, and our satellite will appear as a point source. So you'll probably right away figure out that this is a much more efficient way of doing space surveillance if you're interested in tracking dimmer objects. Why? Well, instead of dispersing your precious photons all over a line, over several hundred pixels, we're now concentrating the pixels from our object into just, or the photons from our objects onto just a limited number of pixels, meaning we can detect fainter objects that we could if we used SSM. So this is what it looks like. You guys are all familiar, so I'm not gonna spend too much time here. Every time I tell people that I do space surveillance and use telescopes to track satellites, they say, "Oh, you must see some pretty neat stuff." Fortunately, I've never seen a spatially resolved satellite from this type of imagery. Essentially, they all look like white dots. So what do we do with these measurements? Well, I told you that we track, right? So we update first and foremost when we do space surveillance. I'd say that until recently and even now, the bulk of this mission is to update the orbital elements. Essentially, we're basically observing and comparing to what was the previous position, and we update that, and then we update the CAD log. In the last, I'd say 10 to 15 years, we've been also using the photometric measurement to essentially characterize the object. And when we mean characterize, not very different than identify. If I look at a picture of, let's say I've got, I'll say Jim because you're the only one that I personally know. But if I look at an object, a picture of Jim, I can identify it, right? Because if I've got spatially resolved, I've seen his face before and I know, yeah, that's Jim, I can identify it. If I start making the image a bit coarser, then I've got more difficulty in identifying. If I can recognize some features of the background, if I recognize that, yeah, he's got, the color of his hair, the tone of his skin, perhaps he's, he's wearing a uniform that day, I can say, well, I'm characterizing, right? I'm starting to define features in the image that allow me to potentially lead to an identification, or I'm limited at, yeah, maybe this is Jim, or maybe this is someone that looks like Jim. If I build a historical database of these image set and I combine it with other stuff, so if I get, like, I can hear snippets of his voice, if I know the location where these images were located, I can now use that characterization data set that I've got, use it with other incomplete data set to identify. So that's what I mean by characterization, amassing data to be able to eventually lead to identification. We can also use characterization to sort of keep track on an object. So here what you've got is a light curve of the Galaxy 15 geostationary satellite. It's got, it's got two bright peaks. So over the course of the night, it's going to start dim, it's going to become brighter, it's going to dim out again, it's going to become brighter, and that. So I can keep following this guy, maybe not night after night, but week after week. And then if something happens, or if the light curve changes, then I can say, oh, something happened tonight. And if I've got other pieces of information, I can then tie, maybe they're doing either, they've changed your antenna orientation, or maybe something else happened. They've, if I start seeing a sort of a cyclical light curve, I can tell, oh, this satellite is tumbling. They've either lost the system or they've got a catastrophic failure. And some of you might be familiar with light curves. I mean, light curves have been used by the astrophysics community and even, the general astronomer community to do light curve of, asteroid rotational periods, binary star system, and now, exoplanet transits. So I'm pretty much anybody can do that. I've, with one of my fourth year students in 2014, essentially from using a 14-inch telescope, we essentially observed an exoplanetary transit, which at the time I thought was pretty cool. So we can use characterization to compare other satellites. So this is a plot that was created by a friend, my colleague at DRDC, Dr. Lockie Scott. And essentially he decided to compare the light curves of different satellites. And he came to the conclusion that satellites that have a similar bus, similar structure, will have a similar light curve. That can be used if you're looking at a new object and you're not sure who this guy is. If you look at its light signature and you can match it up to something in your catalog, you can say, well, I don't know what that is, but I know it's using this type of satellite bus. So these are the uses of characterization. So that said, that brings me to our experiment that we started, almost 9 months ago. And the focus of this experiment was an opportunity that we saw at DRDC. MEV2, so Mission Extension Vehicle 2, is a satellite. It's a servicer that was launched on 15 August 2020 to go up in space to a geostationary orbit and essentially dock onto Intelsat 1002 that you see to the right of my slide here, and essentially dock with it. And for the next 5 years, MEV2 is essentially going to provide the propulsion, I think the power, but some of the basic services that Intelsat 1002 required to extend its lifetime by 5 years. After that 5-year duration, essentially, I believe MEV2 is going to bring Intelsat 1002 into graveyard orbit, and then it will go on to its next satellite to be serviced. For us at DRDC, this was an opportunity for us to observe how the MEV2 servicing mission was going to affect the Intelsat 1002 light curve. And specifically, what I wanted to observe was whether I could detect if someone comes up very close to Intelsat 1002, makes changes to it, would I be able to detect it? So that was my question. You'll have my slide deck, and if you're interested, I won't show it tonight, but if you click on that little here sentence, this takes you to a Northrop Grumman video that shows you the MEV1 mission profile, which is essentially very similar to the MEV2. You see everything from launch to the simulation of how it goes on and docks with the Intelsat the Intelsat spacecraft, which, you know, if you're a geek like me, it's pretty cool. So without any further ado, I'm going to give the floor to Jim to talk about the experimental setup.
All right, thanks, Don. So when Don approached me, we actually had a couple of different options available, and this is what we ended up deciding to go with. We decided to use my Explore Scientific ED127, which is an airspace triplet refractor. It has a focal length of 952 millimeters, and its speed is at f7.5. The imaging camera that we chose was the ZWO ASI 183mm Pro. And I believe the reason Don may have chose that, and you can correct me if I'm wrong, is the super small micro, or the pixel size, 2.4 micron, which gave a really nice size and resolution. As well in there, we have the filter wheel, so we could use the different filters. Initially, we were going to be using proper photometry filters, but due to COVID, unfortunately, supply and demand, as everyone knows, was an issue. So we eventually just decided to go with the astrometric imaging filters that I've been using for doing some astrophotography in the past, and we decided on the RGB set. So with the camera and the scope combined, that gave us a resulting field of view of just a little under a degree by a half a degree. So just to give you an example of what that would look like, you can go ahead to the next slide there, Don.
Sure, for some reason it seems stuck. Oh, there you go.
Oh. So this just gives you the field of view that we're working with, the size of the field of view. So these are a couple of images that I took last year or the year before, M81, M82, with the exact same setup, with the same scope, camera, and filters. And just some additional equipment. Everything was riding on a Skywatcher HEQ5. That was not my original plan. My original plan was to use my Ioptron CEM60, but Murphy had other plans, as usual. I think a week or two before we decided to start everything, I had problems with my mount, so I ended up getting in a bit of a panic and reached out to a really good gentleman named Dave up in Ontario, who owns a company called TPI Astro, and he quickly made me an adapter for my HEQ5 so it would fit on my pier that my CEM60 was sitting on. So that solved that problem right quick. Just some other things there. We used there's an Intel NUC PC that's riding on top of the scope. Everything is remote powered by a Pegasus Ultimate Power Box. The guide scope is just a little 30mm ZWO guide scope with a ASI 120mm mini guide cam, moonlight focuser, and of course 2 straps. And this just gives you a relative idea of the inclination, that's probably not the right word, the altitude of the satellite from my backyard. It's very, very low on the horizon. I think it's 16 degrees now.
Yeah, it is.
From my location. So, I mean, you can definitely see why Don reached out to an observer on the East Coast. There's no way that they would have been able to see this past, probably like west of Halifax. Would have been very difficult. So. And that's it for me.
All right, thank you very much, Jim. So the objective of the experiment, so got some feedback, sorry. So the short-term objective was to assess whether light curves or time-resolved multicolor photometric measurements could be used to reliably detect and characterize the docking event. So essentially, I wanted to look at Intelsat before, during, and after, and I wanted to do so not just with the visual band like we typically do, but essentially in multicolor. So ideally, I would have liked to use BVRI, Johnson Cousins band, and do something like you see on the right. So the results that you see on the right were collected by me using a spectrograph at the 1.6 meter telescope at the Observatoire du Mont-Mégantic in southern Quebec. I went there in 2014 and obtained 7 nights of observations using that instrument. And what I did is I looked at the Galaxy 11 satellite and essentially collected spectra. And I heard someone talking about spectroscopy earlier on, contrary to photometry, where you get one point source. With spectroscopy, you essentially get, well, in one direction, you get the spatial direction, but on one axis, you get the wavelength. So using that and then the spectra, multiplying it by the filter bands, but in this case, these were mathematical filter bands, I was able to use my spectra and do sort of simultaneous multi-band photometry with the object. And what you see here, the black dots are the light curves that we traditionally see in the V band. And then the color dots that you see are color indices. So basically taking the blue light curve minus the V light curve. So that gives you the blue dots. Using the blue minus the R and so on, all the way R minus I. And what you see is, or what we observed during that experiment, is that although that light curve is somewhat boring, it sort of starts dim, goes high, and then back down, back high, it changes color. That showed us, and it's not surprising when you think about it, but the light reflected off the satellite changes colors, and that makes sense, right? At one point we'll see light reflected off the solar panel, which will appear a bit more blue. At other times we'll see the light reflected off the MLI, so the multi-layer insulation, that gold covering that we typically see on satellite. And at other part, it could be reflecting off the antennas, which are either white or aluminum made and so on. So I wanted to try and reproduce results like that, but instead of using a 1.6 meter telescope and a spectrograph, I wanted to use commercial off-the-shelf, small telescope like we'd be using at DRDC. The long-term objective, I wanted to develop and test observation procedures and data technique for doing this efficiently. This is still pretty much brand new. It's still in the realm of research, but I want to come up with the tools and techniques so that eventually you don't need to have a science degree to collect the data and process the data. Ideally, we'd want to have our men and women in uniform to be able to do this using their D&D operated telescope. And then finally, the long-term objective of this is to assess the military utility of doing this. Sure, I can produce nice plots like this, and for a geek like me, this is exciting. But if it's not worthwhile to the military community, to the government officials to inform, some decision maker, then there's no point in doing it. So I wanted, the long-term objective is to see, is there value in doing this? And then the secondary benefit in all of this, I talked about Jack Warrow, my student from York University, who's working with me. I asked him to develop the image processor using open source software, Python, that's available online. And the goal here is that eventually in the future, if I'm successful, I'd like to make this available. Anybody who wants to do this or wants to collaborate with us, instead of having to come up with your own tools to process the imagery, I'd like to be able to say, here, there you go, take the tools, and then we can focus on actually analyzing the data that you see on the right side of your screen. Jim's already given you a much more detailed breakdown of the experimental setup. I still wanted to show this because I've already presented preliminary results of this experiment twice now at international panels to our Five Eyes allied, so US, UK, Australia, New Zealand, and us. Every time I talk about the setup, I make a special point to say that if I were to venture, I'd say maybe 50% of all images were collected when Jim was not located at his house, but right there somewhere in the Atlantic, which I find phenomenal. I'm jealous of the setup, and I wish I would be able to do the exact same thing. Everybody that I've talked to, or whenever, every time I have the chance to talk about this project, everybody's amazed, and as they should be. So here are some preliminary results. We're still going through the data. You know what? I just realized I didn't even show an image of the satellites, but in a typical frame, we'd see 4 satellites or 4 dots, a bunch of streaking stars, 4 dots. We'd see Intelsat 1002, MEV2, and then we had 2 other geostationary satellites that were just there for the bonus, Tor 5 and Tor 6. This is the photometry. So essentially all 4 objects had different light curves. So this is, well, in my opinion, fantastic. If you look at the blue dots, that's your Intelsat 1002. Essentially, it starts off here. The scale is instrumental magnitude. So I didn't bother putting in an arbitrary 0 point. We're just using essentially instrumental magnitude. We're in the process of converting this into standard magnitudes. But essentially see that the satellite will start off with sort of a pretty boring light curve. This is a period of eclipse. So during the springtime, near spring, and the fall equinox, essentially geostationary satellites will be in eclipse. Then when it comes out in eclipse, it gets brighter, and then it's got a sort of like the Batman sort of ears, and then it's going to dim out. Very different than the MEV2 light curve, which essentially peaks and then just progressively goes down. And here, if you look at, 3 o'clock UTC or Zulu, essentially something happens. If MEV2 were the only one in the field of view, I'd probably say, okay, clouds were passing by and we lost something there. But we're seeing, because of the other satellites, they're not dipping in magnitude, in brightness. So whatever's happening in the light curve is not because of atmosphere. It's something to do with the satellite. So part of the analysis, earlier when I was saying I'd like us to not focus on the tools to process the imagery, I want us to focus eventually on analyzing the results. This is what I want to analyze. Why is it dipping there, and why aren't the other ones dipping? What happened to the satellite that it did this? So now I talked to you about, we're collecting data in 3 bands. So we did our color or time resolved color indices. So the black curve is essentially the G band, green band light curve of the Intelsat 1002. And then below you'll see the time resolved color indices. So this is how it changes color over time. And to be honest with you, I was surprised. I was very surprised. If you think back to the results that I showed you with Galaxy 11, the color indices were not all over the place, but they changed a lot over the course of an evening. And this is more or less constant. And at first I was worried. I was thinking, okay, I didn't use BVRI filters. Shouldn't matter, but and I was trying to think of what went wrong. And then when we presented the first time to our colleagues, the Brits, they've also been observing 1002, and they came to they had similar results, that the color indices basically didn't vary all that much. I mean, you see some variations here and there, but nothing that pops out of the ordinary. So it was a bit comforting to know that we're not the only ones to observe this. So that means we collected the data right and we processed the data right. But now we've got to analyze, why isn't it changing color, especially when it gets brighter. You'd expect at that time that you're getting more light from the solar panel, so you should be getting more blue light. So these color indices should be changing there. It's not too sure what's happening. This is the time resolved color indices of the MEV2. And as you can see, there's not a whole lot of changes there, but right before we enter eclipse, there's a color change there. And then more interesting, what really gets me going, if you look past 0300, as the satellite dims, you can see now a change in color. So this is good. That means, I was expecting a change in color. We're now analyzing, trying to figure out what that actually means, what portions of the satellites were actually reflecting light at that time. Oh, I didn't show, I had a well, I forgot to put in the figure. We do have a after docking event, and the light curves are completely different. So the pre-docking event, when we look at the Intelsat 1002 light curve compared to the post-docking event, are very different. So the first objective of the experiment, can we detect change? Basically check, we've done it. And now we're moving on to the secondary objective of trying to evaluate, military uses of this, lessons learned, and all. So future work, well, we've got to tidy up our image processor. That's probably going to take a bit of a time, but for the purpose of the experiment, I think we're there. We need to process all of the observations data set. We focused on a few specific nights. We have to go back and process everything. And so that's probably going to take us a bit of a time. And we've got to be able to, as I said, go from instrumental magnitude to standard magnitude. And that's going to allow us to compare our results with our colleagues in the UK so that we can compare apples to apples. We're going to write a report. It should be publicly available. And when I say publicly available, the RDC, actually, there's a website somewhere that, you can probably not Google, but if you punch in the title, you can actually read the report. So if any of you are interested in the future, you'll certainly be able to read it. Well, Jim and I have plans to do a second contract for observations, to do follow-up observations between September of this year up to March of next year. And the objective is going to be compare, last year to this year, essentially, and see what the changes were, and go a bit perhaps deeper into, okay, we've detected a change. What is the magnitude of this change? What is the nature of this change? So that concludes the presentation for me. I think in closing remark, for me, this has been an exceptional experience. Well, the experiment's been fun. As a scientist, I love doing this type of stuff. But on a personal note, I met, well, I think a friend. I found out about a new place. And hopefully one day I'll be able to actually go down and well, see that observatory and see the new one that you're building, Jim.
Perfect. You're more than welcome.
So I went over time for that. I apologize. Are there any questions?
I don't need to apologize. Anybody got any questions? When you were talking about the early days of D&D and the bunker satellite tracking cameras, I had a friend who worked on them, and one of them, the one that was in Cold Lake, is now operating refurnished with a CCD camera at the Calgary Observatory, University of Calgary, searching for near-Earth asteroids.
Yeah.
So nothing ever gets thrown away; it gets reused.
No, you're absolutely right. Would that friend be, man, I forgot his name.
That's Ellen Hildebrand.
Yeah. Well, actually, I worked with him. We collaborated on the NeoSat mission, so I like to think I know him well. So.
Yeah.
He's a good egg. But actually, the guy, besides Alan, the guy at the military was a sergeant who would go out at night, print the film, develop it, circle what were satellites, and then would have to send it down to the U.S. military.
Yeah.
He worked with me for about 10 years after he got out of the forces.
Okay.
That was kind of interesting. Any questions? So, I think we got everybody stumped. Oh, you can unmute yourself.
Okay, yeah. Interesting. I was just wondering if you could tell me why docking events were chosen as a kind of to see, you know, whether you could detect change, as far as I can gather from what you were saying. So why did you choose docking events? Was it just something that you thought would be an obvious way of detecting change in the satellite's behavior and light reflection, or is there something else that is of interest?
That's a great question. The scientist in me, just out of interest. I've been looking at light curves for a long time, and I wanted to see, you know, would I be able to detect a satellite docking with another one?
Okay.
As a defense scientist, the interest is, if you think back to what I said about on-orbit servicing, there's a lot of good, you know, that can come out of these. We can now extend the mission of geostationary satellites. So Intelsat 1002, if it had not been serviced, I would imagine probably had a year left in its lifetime at most. Now, because of this, Intelsat can use the satellite for 5 more years. So it's got a higher return on investment.
Yeah.
The flip side to that is that, you know, this type of technology is what's called dual use technology. So if we can use it to go service a mission, we could potentially use this type of missions to go inspect a satellite, right? Or we could dock to a satellite and make changes to the satellites, you know, if we were in a conflict, or if we've got a confrontational and adversarial situation. So we have not seen that yet, fortunately. However, you know, if you look at space news, or if you look at the events that have occurred since, I believe, 2014, the first, you know, it wasn't a non-orbit servicing, but the first sort of proximity operation that was highly public was a Russian spacecraft that essentially visited a bunch of geostationary satellites.
Right.
That made a lot of commercial satellite operators uncomfortable because, you know, you're coming up very close to me at very high speeds. I mean, the speeds are relative, but nonetheless, a collision at 3 kilometers per second can, you know, spell disaster. So from a military perspective, from a defense perspective, you know, we're always planning for the worst, right? If you plan for the worst, then, you know,
we hope it doesn't happen.
You hope that it doesn't happen. But if it were to happen, would I be able to detect it? Would we be able to detect it?
Yeah.
And if so, how would we detect this? And from that information, what type of information do I collect? And then what type of information do I feed to decision makers? So the men and women in uniform that makes the decision to decide, okay, how do I act upon this? And before they act, they need to be sure, very sure that, you know, something bad has happened. So this is why we're doing this. We're sort of learning how to do it and what information to provide our military commanders and senior government officials should something bad in the future happen.
Thanks very much. Thank you.
Great. Mark, you had a question, and then Doug has a question.
There. Yeah, my question is, how optimistic are you that we can avoid, I guess, massive collisions in space? Or are we doomed to have that Hollywood scenario where everything becomes a chain reaction?
That's all.
That's a great question. It's a hard one to answer. I think I tend to see the glass half full. So I think I'm positive that we're taking, and when I say we, the international community. So like I observe stuff. I'm not one of the policy people, but I feel confident, that the international community is taking the right steps to prevent these types of collisions in the future. If you look to the US, a few years ago, they stood up the Office of Space Traffic Management because the US government is taking, the risk of collisions, the increased traffic very seriously. And this was starting to be a bit too much for DoD, the US Department of Defense, to manage on its own. And it's actually not their mission. So now they stood up this civil agency, or I don't know if it's officially a civil agency is the right term, but a civil organization within the US that is going to look at space traffic management. Other countries, other nations around the world are following suit and are looking at this problem seriously. How do we manage it? They're coming up with policies to make sure that, rules of the road. What do we do? And, when I alluded to the deorbit policy, that 25-year rule that after you finished with your space mission, you got to deorbit, that's a step in the right direction. Are there going to be collisions? Realistically, probably, yeah. We are going in the right directions. Are we going fast enough? Not too sure. Maybe, it'll take another collision or two for people to start moving even faster. I am optimistic, though.
Thanks. Yeah, we cross our fingers. Doug asks, is satellite design changing in response to surveillance and congestion, non-reflective surfaces that will deflect debris, larger stores of propellant for avoiding collisions and deorbiting?
That's a big question. It's a great question. So are we improving our satellite, the way we build satellites? So the first part I heard was to make them more reflective or less reflective. In fact, yeah, shortly after the first Starlink spacecraft were launched, actually a friend of mine, Dr. Patrick Seitzer from the University of Michigan at Ann Arbor, with a group of his colleagues, basically set up a committee, I think was requested, or they've got linked to SpaceX, trying to address how their plans for a mega constellation would affect professional observers, so astrophysicists using these multi-$100 million observatories on the Earth to do these studies, and then their images or their observations can be ruined by this train of satellites that pass through their exposures. In response to that, SpaceX actually designed darker satellites or less reflective Starlink satellites, and they've been in orbit. And actually, my colleague at the RDC Ottawa is characterizing these Starlink satellites. The next part of the question, are we building satellites better so to minimize space debris? That's outside of my field. But the answer to that would be yes. I think there is, we're including propulsion now or ways of deorbiting satellites. UTIUS, Canada's own University of Toronto, a few years ago launched the Canik 7 CubeSat, and they basically tested a drag sail. And the idea here was that not all satellites are going to have propulsion system. They're complicated, they're complex, they're costly, and on small satellites, not many universities are going to go that route. Could we put in a passive system such as a drag sail to allow the CubeSats to deorbit? And so, yeah, design satellite is being influenced by, the desire to leave less stuff out there.
Robert would like to ask, how does one go about making a telescope that's going to track a satellite so to image it Standard mounts do not do this. That's just an engineering problem, really. How to make a telescope track a satellite?
Well, if you've got most robotic mounts nowadays will track satellites. So you basically have to have the gear system or the mount that's capable of slewing fast enough. But even in that case, like for geostationary satellites, a friend of mine at RMC, he was doing his PhD at the same time as me. He basically was using, can't remember his mount, but it wasn't something spectacular or very expensive. He was collecting photometric light curves of geosat. What he'd do is slew, and then he'd just shut off, like literally shut off the mount, and then just observe all night. For GPS, they move very slowly across the sky. So even, mounts that were made to track stars will be able to track that. LEOs are a bit challenging, if those that cross the sky in about 2 or 3 minutes. But most commercial mounts like the software Beast, Paramount will track LEOs. So the mount is one thing, and then the software, right? The SkyX, I just received, they sell a strong, can't remember the name of the mount, Edge, StarSense, Edge something mount, and apparently it can track satellites. I'm still figuring out how to align it, but I think nowadays you can get good mounts that allow you to track satellites.
Okay, can you hear me, Don?
Yep.
Yeah, I was just wondering, different satellites may have different speeds. So if you're trying to image a dim satellite whereby you want to keep it centered in the field of view, then the mount would have to have, would you have to have a special algorithm for each individual satellite in order for that to be able to track any particular satellite?
So no, if your mount can track with satellite, and typically what the software is going to ingest are the 2-line element set. So I use the SkyX, so we use the SkyX with our Paramount. Software Beast built the Paramount, and they also built the SkyX software. So the SkyX software ingests 2-line element sets that you can automatically download them from SpaceTrack, or if you've got your own TLE, you can basically, and you don't have an internet connection, you can actually load it directly into SpaceX. And if you can track a satellite, you can track any satellite. There's 2 types of strategies that you can use to track a satellite. The easiest one, which has got perhaps not the best results, is the open loop tracking, right? So basically, you're just going on the TLE. So if the TLE's off, you might think that, yeah, I'm tracking it based on the TLE. So your telescope will be exactly where the TLE says it should be. But if the orbit changed at all, the satellite might not be there. And it's not going to correct for that. A closed loop tracking, essentially, your image essentially track again on the TLE, but then once you're on the satellite, you can then center your satellite and then process the imagery, or process the imagery almost on the fly, so in real time, essentially, and update the position of the satellite in the image, and feed that refined information to the mount so that you can make slight correction. Again, my colleague, my friend, Lockie Scott at DRDC, he's actually implemented a we used to use the open loop tracking with our Paramount at DRDC, and Lockie just a few weeks ago implemented a closed loop tracking. So using MATLAB, a bit of code, he processes, he basically, downloads an image, does the plate solution, finds the astrometry of the satellite, where's it, he brings it to the center of the field, and then the telescope is going to adjust itself. Does that answer your question?
Yeah, it does. Yeah, we actually use closed loop when we do auto guiding. something called auto guiding where but there would be limits to, your off-the-shelf store-bought auto guiding, that if you were trying to do that with satellite that was moving at a relative speed that would be outside of what that piece of software was expecting, then, I guess that's where you get your mathematics people involved to tweak that type of scenario. Okay, thank you.
Actually, if you Google PlaneWave, they've got a video out there with one of their CDK mounts where they're tracking a low Earth orbit, quite low Earth orbit. And that thing just stays in the center. It's actually pretty neat to see. It's got me mouthing at the mouth.
Mike asks, what's the brightest geosync satellite we can see from here? The brightest geosynchronous.
It's going to vary. So as you saw over the course of the night, right, you're going to go typically from magnitude 13, 14 up to magnitude 6. Sometimes you could potentially go a bit higher than that, magnitude 5. So but it would be these glints, and for very short periods of time. So for geostationary satellites, I mean, with telescopes, a bit of a longer exposure time, typically anywhere between, well, what were you doing, Jim? I think 10 seconds. We were doing 5 or 10 seconds.
5 seconds.
5 seconds. And I mean, you can spot these things right away. There's iridium flashes. If you're not familiar with those, if you yeah,
Oh yes.
so they're pretty neat to watch.
Kaboom.
Yeah, and then the LEOs, right? If you go out an hour after sunset, an hour before sunrise, and just put up your head, you'll see these. Well, they look like stars, right? There's no flashing red or green light, so they're obviously not a plane. They're not making any noise, and they just whiz by. That's a LEO, and these are bright. I mean, the ISS, I believe, is probably over 0 for sure.
All right. Thank you very much, Don. Really appreciate it.
Thank you very much. It was a
Talk.
pleasure.
Uh,
Thank you to Jim.
and to Jim too, I forgot.
Perseverance.
A lot of work, especially from the middle of the ocean nowhere.
So Gary, next I had, if you have any Astronomy Day report you wanted to make, or?
No, I wasn't going to make an Astronomy Day report
Okay.
tonight.
I'll refer people then to our website under outreach, past public events. There's a short page there of some pictures. That was our first COVID public interaction, and with limited success and some other problems. But after that, I have observations and photos, or do you want to do Nikolai first? Do you have very much in the way of observing and photos?
I only have 5 people.
Okay.
5.
How long is it going to take you?
I don't know. You want to do Nikolai? You want to do Nikolai or me? Either one. We're both long and boring.
I'd like to do Nikolai first.
Okay.
And
He's
he's
more
not-
boring.
He's never boring.
Thank you, Randy. All righty. Let me ask first. The observing challenge for last month, which was to see Mercury and the Pleiades together in the sky around May 3rd. We did actually get a clear sky. At least one of those evenings around that date was clear and the others were partly clear. So I'm curious to see if anybody was able to see that. And if you did, what did it look like? Was it difficult to see? What did you see, et cetera, et cetera?
It's actually easier than I thought it was going to be.
Yeah, Jim, I know you're at least the only or one of the very few people who I know that saw it, and you took a picture of it.
I didn't take a picture of it. No.
Oh no,
But
somebody
I-
else did.
I was kind of surprised actually when I went out to do it. But I was watching this bright star in the sky, which obviously wasn't a star. I thought it was Venus at the time until I come to realize a little later it was actually Mercury that I was watching the whole time.
Yeah. Well, I didn't get a chance to get out on the clear night, but I did on the next 2 nights when it was partly clear, and I did see Mercury and Venus very clearly, but I did not see the Pleiades because of clouds. I actually, well, I was going to share my screen to do the what's up anyway. So I'm just gonna do that, and I'm gonna show you my picture. Okay, so this needs to go away. So can you see my screen?
Yes.
So
Very nice.
what happened here was it was pretty clear. I think this was on the 4th. So if I zoom in here, right here, this is Mercury. But it wasn't dark enough to see the Pleiades. And by the time it got dark enough, these clouds had gotten much thicker and bigger. And this was from Signal Hill, of course. As you can kind of tell, this is Deadman Spawn. So this is Mercury again, but it wasn't dark enough. And then, by the time that happened, it was really low and it was cloudy, and I couldn't see the two together. But so that was my experience with it. Did anybody else see that at all?
Hello, hello, hello.
Hello.
Hi, Nikolai, this is Jim.
Oh, hi. Yes, this is Jim. Yes.
Yeah, Jim S. Yeah, yeah.
Right.
I just wanted to comment. I was out taking pictures of the moon just now, and it just dashed in, and I caught this conversation about the Mercury and Pleiades. I did manage to get out on the Sunday night, and I did get some pictures with my 500 millimeter. I think it was 500 millimeter. I can't recall. No, it was just a 200 millimeter telephoto lens, and I was able to stack them, and I was able to do some post processing to actually increase the exposure for the Pleiades, so I can actually. But it doesn't make for a very impressive photograph, but it does document the capture of the Mercury visiting the Pleiades. And I think there was about 4 degrees or 5 degrees separation between Mercury and the Pleiades in that picture.
Is that the picture you shared on the talk list?
I shared the raw file. I have post-processed that in the meantime, and basically boosted the Pleiades and Mercury by a couple of stops each, so that you can actually see them in the picture. So I have improved that particular picture. And so I also did a reverse analysis. I was able to stack the images in PixInsight, and actually did a negative of the sky, and I saw about, and I'm just going to make this up now, I'm approximately 40 of the stars in the Pleiades.
Well done.
Nice.
It was a great challenge. Thank you very much for proposing that. I never would have known otherwise. So I thought that was a really great challenge.
Yeah, that was, a tough one, especially where you had a short window to see it and it was close to the horizon.
Yes, I estimated that I had about, as it got dark, I had about 2 or 3 or 4 minutes in which to capture everything before everything set.
Yeah.
And so it was quite a challenge, actually.
Oh,
So
yeah.
I'm actually quite proud of that, actually. So,
Nice.
so thank you for that.
You're welcome. I'm glad people are enjoying these. Wait until you see this month's.
Oh,
No, it's actually, well, you'll see. Okay, so assuming nobody else has seen it, I will continue on with the sky this month. And this is, of course, up on our website, and it shows what you can see here over the next month. So these are the sunset and sunrise times for today. Sunset is pretty late at 8:37. We're about a month away from summer solstice, so we'll gain another, I don't know, 40 minutes total of daylight or something by then. And then we have planets rise and set time here as well. And then we have the most recent picture of the sun. And as you know, it's been, seeing more activity than we've had for quite a while. And right now there's actually a very, very hefty sunspot group emerging here and about to rotate into view. Associated prominences as well. And I know people have been looking at the sun and posting some pictures as well on the talk list. So that, that's great to see that sun's getting more love as of recently. Now, here comes the observing challenge, and that is the solar eclipse. Now, seeing the solar eclipse itself is not difficult astronomically speaking, but in our circumstances, it's going to be difficult meteorologically speaking. And the reason for that is that the solar eclipse, which will be it's an annular solar eclipse, but it will be partial in St. John's. It occurs early in the morning, which, to see the sun near the horizon in the morning in June, where, during the summer, usually mornings are cloudy or due to fog, and especially, looking kind of east, it's going to be a challenge, and you only have a 2-hour window to see it. So this is, these are the details of the eclipse for St. John's. If you're somewhere else, it's going to be a little bit different. But sunrise is at 5:03, and in about an hour, the eclipse starts 6:05. A maximum occurs at 7:05, and that will be 65% obscured or coverage. That's the maximum from St. John's. And then it ends at 8:10. So just over 2 hours opportunity to see it there. It'll be great to see it. I think the last solar eclipse we had was in November. It was a small partial eclipse in November that I can't remember the year, maybe 2014 or something. It was cloudy. We didn't see it. And then, so this is, a great opportunity for us. If you want to see annual, you have to go to Northern Ontario, basically. Good luck with that. Now, planets, evening planets, we have Mercury, which is currently visible, but it will become a morning planet in June. And we also have Venus, bright evening star. And we do have Mars as well. Fairly bright, but pretty small, so you won't see much with a telescope because it's pretty far. And we do have the morning planets, Jupiter and Saturn, rising, 3 to 4 hours before the sun. So they do get high enough, for you to make meaningful observations. Comets, nothing spectacular to talk about. asteroids, the usual stuff. Supernovae, brightest one is 11.8 magnitude, so nothing too bright. There aren't any meteor showers right now. And here's a list of your deep sky objects that are best placed, both for telescopic and binocular observation. This is in May, this is in June. Here are some ISS passes, plenty this month, and then they kind of end for a while in early June, and then they resume again later in June. Observing sessions, of course, not happening, but here are the observing calendars for May and for June as well. And that is all I have. Are there any questions?
Anybody know, or anybody have software that can predict where the greatest amount of eclipse is on the island?
I know that annular occurs further west, so I would imagine that the further west and north you go, the more coverage you'll get, but I don't think you're gonna get.
It's not a big difference.
Yeah.
No.
No. Time and date has it. You can just change the place, right?
Yes, time and date will do it, yeah.
Like
Yeah.
I looked at it and there's not a whole big difference.
Yeah. Just wondering about an early staycation in San Anthony.
Oh yeah. Well, that would be a good spot, I would think, but you'll gain a few percent there, but that's about it. I don't even know if you'll be able to tell.
No.
Well, Stellarium will do all that for you. I mean, there are several star programs that will do all that for you. Change your location.
Sure.
Okay. Gary, that leaves you 10 minutes. Is that enough?
Oh, yeah, geez.
Okay, Nikolai.
All
you
depends
finished?
on how fast these people, you want to share your,
Thank you, Nikolai.
first one up will be Jim. Mike,
Yep.
are you there?
Yep.
You want to talk about this one?
Yeah. I think actually it was March. Oh, it's not March.
This one is March 25th. This is 65, 66.
Oh,
This
so
is
this
not
one's
M1.
from last month, looks
Yeah,
like.
yeah, I've been having trouble downloading off my mail. So.
Oh, okay. Yeah, so this is the Leo triplet. I'm not sure how, it probably was about 20 minutes exposure. Just from a backyard with the 80 millimeter. So that's sort of the story about that one.
Okay, I got it. This is your M80 182. I couldn't get you 104.
Oh, okay. Yeah, and it looks like this one is the thumbnail, not the one I emailed, but it actually looks better than that in the picture. But so this one would have been about April 30th, looking almost straight up. And the other one I did was M104 on May 5th, and M104 is near Virgo, and it's the Sombrero Galaxy, and I didn't do that on purpose on May 5th, but it turned out it was on May 5th. Okay.
Yeah, thanks, Mike. Okay, Robert Babs.
Oh, is that me?
Yeah, that's you.
Are you sure of this?
That's
Oh.
you. It's the Leo triplets. 1, 2, 3.
Oh,
Field of view is with my 400 millimeter lens.
or- Okay, yeah. And this is all with a camera lens that, you know, in full frame DSLR, then field of view is going to be huge. And I was surprised that came out as well as it did, considering the equipment that I was using. But that's the triplets as well.
Is that out in Butterpot?
I'm not sure, Gary. I wasn't expecting this to be on tonight, or I would have taken a closer look to see where I actually took it. But I would say it probably was Butterpot, because I don't think I could do that from.
I think it was, Robert, you went out by yourself. It was a nice
Okay.
quiet time, I think you said.
Yeah, well, that would make sense because I'm not using any filter, so I don't think I could get that kind of darkness, if you will. It should be all fogged up with no filter in use in the city. So that would be from Butterfly, yeah.
Okay, thanks, Robert.
Yeah.
Jim, this is another one that didn't come out good. Are you there, Jim? Jim Johnson? Yeah, yeah.
All right. Yeah, so this was taken on the night of the 29th of April. The same setup that I use for the spectroscopy that we just presented on. Same telescope, same everything. Yeah.
Okay, I think
5.5 hours exposure from the backyard. And apparently this is Chris's favorite galaxy. I did not know that.
very good. Thanks very much. I think that's it for me. Yep. Okay. Stop sharing. Sorry about the quality, guys. It seems like my Rogers account is giving me a lot of trouble. When I downloaded 104, it disappeared. Okay, what's left on the list as we say goodnight? Randy.
I wanted to mention that the AGM for the RESC is coming up again on the 25th, 27th of June. You don't have the register for the AGM, but you do for the GA.
What's the price again?
It's $15 plus tax, I think, something like that. If you want to see, go to the RESC website. There's a link for the AGM 2021. All the documents are there, the agenda and last year's minutes, all that sort of stuff. I wanted to mention that we may try to do something for the June 10th solar eclipse. We were playing around up on Signal Hill on Saturday to see, and we quickly learned that any kind of covering on your display or monitor subject to wind pretty quickly, right, Mike? And it's very tough to see in a bright sunny day. So maybe we'll have the best of both worlds. Nikolai will give us a foggy morning, just dark enough so we can see the eclipse, but not that we'll be blinded by the light, right?
Yeah, if you tape your shade to the table has to be heavy enough that it doesn't blow away.
Yeah.
With your computer on it.
Yeah. A full case of antifreeze helped that, right, Mike?
Yeah.
So
that was the heavy one.
Yeah.
Let's check the difference between here and St. Anthony.
Snantony by Snantony.
So 65% here and 72% in St. Anthony.
Oh,
we're gaining 7%, not bad.
Yeah.
12-hour drive.
Yeah, 12-hour drive.
0.5% an hour.
Yeah.
I would say better weather there too.
You might see some icebergs up there too.
Yeah.
No icebergs.
I should point out that the whole planet seems to be almost ignoring the Chinese have finally landed their probe on Mars.
So they say.
Well, they've got pictures out now.
Yeah.
Yeah, but it hasn't driven down the ramp yet, has it?
Yeah.
That's not very trusting.
The Americans have found UFOs. Haven't you seen that?
Americans find UFOs everywhere they look. I think they build half of them. No, no, really. China's first mission to Mars, they got it all right and they landed. And there's a rover there too. They're the only ones to have gotten the whole package to Mars in one flight. They're the only ones to land on the first try.
But they
think
stole,
the,
they stole all the technology though.
I think the first picture came out today, didn't it, of the actual lander on the surface? Yeah. So
yeah, there's one from the rover just about to go down the ramp, I think, and one from the lander color one.
Maybe everyone's still angry at them for almost dropping a huge rocket on everyone's head.
Well,
Yeah.
but they're very pragmatic. I mean, I think they recognize the chances of it hitting anyone were very, very close to zero.
No, well, it wasn't intentional though. That was not, that was a mistake. That's like a 1960s or 70s era type of mistake to make, to lose control of a major component booster like that. So,
Someone has a fresh bed in the gulag.
yeah, well, not necessarily, but you know, that's a one-off kind of error to make, and it's not likely to happen again.
okay, that's all I have on the schedule, Gary. If
Okay.
people want.
All right, I'll give you 5 minutes to talk among yourselves. Anybody been doing any observing? Anybody been doing any astrophotography? Anybody been talking about astronomy? Anybody buying a new toy? Anybody caused the rain to come and the clouds to come?
Fiber-fed spectroscopy, no one wants to hear about
Anybody
that,
doing
so.
any VR stuff? Let me
Gary,
see if I
you keep up
free.
the-
If Gary stops talking, we can
Yeah.
we can do some. Fiber-fed spectroscopy, and I may be doing some more in a minute, but one of these days I'll talk about it.
What are you doing it on?
The Nova tonight.
Okay. Yeah. There's
Yeah, that's
actually some nice spectrum done on it. I'd like to compare it.
Yeah, I did the Cat's Eye Nebula a few weeks ago, and Delta
Mike's got
Draconis
something to
next
say.
to it as a standard. So I'll be showing all that at some point. Mike.
There may be a public astronomy talk from the physics department in 2 weeks. It's still being worked out, and they would actually like to have a good representation from this group, because it's meant to be, it's an interview for a candidate, and they would like it to be an outreach type talk, and a good response from us could increase the odds of actually getting a professional astronomer in the department.
Oh, that's good. So what's the details? When is it again?
I don't have a date yet, but
Okay.
I told them not, it's the same week we have the executive meeting, so I told them not Wednesday.
Well, it could be Wednesday.
Yeah.
Could be, but it'll probably be
Wouldn't be that late.
earlier in the evening, about 6 in the evening.
Right.
So stay tuned for that. It'll be that week.
Okay.
I also saw that the Public Libraries Board have arranged for some kind of an astronomy for all talk. Gary, it's put off by a planetarium group. I just saw where it was. You had to register for it. Did you see that? Towards the
No,
end
I
of the
didn't.
month.
Nope.
So,
Didn't see anything about it at the library. I don't know.
Planetarium Canada, is there such a thing?
There's a Canadian Planetarium Association. Yeah.
Yeah. So we didn't have any.
Could that be
contact
sort of
with-
like you get bird watching kits from the library? I think there's like some people have made arrangements for astronomy kits, like binoculars and a couple of sky guides and a knapsack.
Oh, look, there's an
for kids.
astronomer.
Young astronomer.
Actually, there's a lot of bird watching tonight. Actually, I think there must be a rare bird around, because when I was doing the walk around the lake, Windsor Lake, there were bird watchers everywhere. Never saw so many cameras and binoculars.
Wow.
So it must be a rare bird in the area. You guys doing anything in outreach? And nobody?
Outreach.
Yeah.
I went up to
Any-
Signal Hill several nights for the challenge, but I saw both objects, but not on the same night.
I got to see Mercury and the Pleiades, but only through binoculars. I couldn't.
We're cluing up. Okay. So yeah, I went to Signal Hill a couple of nights to see. I did catch the very, very thin moon. Must be what, 1.5 day old. I think is the thinnest moon I've ever seen.
That was beautiful, Randy.
Yeah.
Yeah, it was a nice picture, Rand.
Yeah.
So I had other pictures. I got more dramatic ones with clouds on the side and everything because I was aiming for this little thin clear period, and I waited 1.5 hours for the moon to get down to that area. And as it did, they got smaller and smaller. By the time it got down to the top left, right? So,
Not even a toenail moon.
yeah.
You know what the record is for earliest sighting of the moon after new moon? Like how many hours after new moon?
Yeah.
Isn't it like 11 or 13 hours or something?
Yeah, it's
I thought it was 18, but I could be wrong.
the
It's something incredibly low. Yes.
And
Yeah.
and from the equator, or like where the moon is going to set vertically.
yeah,
So the sun's going to
Mus-
set vertically, right? So
I
you
think the
get-
Muslims track that very closely as well, right?
And I think that's who's got the record.
Yeah. Well, it marked Eid and stuff this year, didn't it? So,
Okay, I'm going to end this now, and because in a few minutes, I think I can't remember which center is taking over.
okay, whatever.
Okay.
They
Have fun.
got an
Good meeting.
executive
Thanks for
meeting.
arranging it, Jim.
Cheers. Yep.
Yep, that was a lot of fun.
Thanks, everybody.
Yep.
That was a good.
Thank you all.
Bye.
Nights. Good nights.
Bye.